Hello teammates, it's Mr. Nanini coming to you with another Physics Bunker production. We're going to look at what I call FRQ6. So I thought about renumbering these and getting on the system, but I'm going to stay. So this is going to be 6 and the next one will be 7 and we'll figure it out. So little conservation of energy, a little free fall, projectile motion. So you're going to read the question carefully, unlike I did, because I was in a hurry to solve this. And then, so use me as a bad example for this one, and I'll show you why. So you're going to read the whole problem. You got a block sliding down. No friction. You had a teammate ask a great question yesterday at the 3 o'clock session. What do you do if something's got wheels? Do you have to consider rotational motion for that? Only if you're asked to. And like I said at the session yesterday, I very assiduously avoided anything rolling in our early days. And just to reinforce that. So this has nothing to do with this problem. I just want to identify that. Block sliding. It's falling. It's going to go some distance d. You're given a height 1 from the tabletop. Two of the blocks released. You're given a height 2 from the floor to the height of the tabletop. And it's an energy conservation projectile motion problem. And just like I worked to model for you in the classroom on your AP exam, which by the way is 2 weeks from today, on your AP exam, ask yourself, what kind of problem is it first? That's going to help set you up. So we're building this skill in these sessions on how to identify the keywords the College Board is looking for. And so if you identify this as an energy conservation free fall problem, you're going to work that vocabulary into your solution. And that's going to give you a more powerful score. So explain why making H1 very small would cause D to be small. Why making H2 very small would cause D to be small. We're going to derive an equation. We're going to explain our choice. And then we're going to look at the moon. That's very interesting. That D is very deceptive. D is a classic AP physics trap. And I'm going to show you why. Let's go. I was very verbose on this, but that's because I didn't read the whole problem before I started solving it. So the first part, without using equations, and there I was, I threw an equation right in there. Basically, you're gonna talk about what I should have done is I should have focused on energy conservation. And if my H1 is very small, my velocity is going to be very small by this relationship. So velocity is going to be proportional to the square root of H1. And I think you can do that, even though they don't say equations. I think the prudent student is going to go there and then there too. I think that's okay. They're not going to get you if you use equations, but you got to use a lot of words. You just can't write by energy conservation this. That's not going to fly. You're going to talk about how H1 determines your final velocity, how H2 determines the time the block is in flight, and you want to answer the question. The question is, why is D going to be small even if H2 is large? You want to answer the question because the velocity is going to be very small and it won't go very far. So answer the question and you will be good. I'm going to refer up to AI related to the combination of factors in AI above. If you're gonna reference another paragraph isolated somehow. So I'm going to use quotation marks. So just so it helps the reader read, right? Again, they're going to spend, I don't know about this year. Typically, they spend about a minute and a half on each question. So you want to make their job easy. We're going to use the same thing. Now we're going to talk about T though. Since T is determined by change in H2, let me label that. I recommend if they label things H1 and H2, you do the exact same thing. Easy money. Change in time, 2 change in H2 over G. You're good. 4 easy points. 4 easy points. B I thought was fascinating. I enjoyed B. I hope you did too. So I kind of set myself up for success. I defined my velocity. I defined my change in time. And I think it's prudent if you're going to answer B. I think it's prudent that you say, you can write as identified in AI and as identified in AII, velocity is, time is. Be specific. Again, you identify that this is an energy conservation projectile motion / freefall problem. Be explicit. Don't think for a second that it's obvious that it's an energy conservation. Even if you stated it up here, you're going to restate it here. This is an energy conservation relationship. I'm going to relate velocity to change in time. Then you're going to work in what you know about projectile motion. The block travels at a constant x velocity when it leaves the table. And you could put in there acceleration due to free fall if you wanted to. I did later. So now what? Oh, I love this. I love this. So identify the velocity in the x is, I could put x there. Velocity in the x is change in d. They use d, you use d. It's good. It's good. Change in d over change in time. You're going to rearrange, again, step by step. Change in d equals velocity x times time. I just did that to help you do the math. Now, so change in d equals my velocity, which is 2gh1. Use your subscripts. Time 2h2 over g. And even under the radical, g's are going to cancel. And then 2 square root of 2 times square root of 2. Square root of 2 times square root of 2 is square root of 4, which is 2. And you're going to put that outside the radical. 2 square root h1 h2. 3 points. Don't be scared of the algebra. The assumption is that you can do algebra. So those watching at home, your eyes roll in the back of your head going, oh my gosh, it's easy. It's easy. The ancient Greeks did this. Hot dog. I'm not belittling anybody, right? I'm not belittling you. The Greeks did this 2,000 years ago. I gotta go because we're out of time. CI write an equation that supports. So to support your reasoning in part A1. So here's where I would have gone heavy in my equations, and I kind of did it up here. Identified in part A1, again, you identified this problem as an energy conservation problem. You're going to hammer that. A small h1 leads to a small vf. You're going to rework this. Even though you wrote it up there, you're going to rework this. You're going to say maybe as I wrote in paragraph AI, you're going to write it again. Small h1, low speed. CII. Similarly, Time leaves the table. Only force acting is gravity. Experiences a constant acceleration. Thus, change in t for free fall can be determined. Change in h2, 1/2 g, change in time squared. You're going to, again, you already wrote it. You're going to write it again. Thus, change in time proportional to change in height 2. Use your subscripts for what height you're talking about. When you're talking about free fall, you can use G. I think it's cleaner as opposed to using A. A is fine, but you can use G. Let's look at D. D is a classic College Board AP Physics trap. I hope that page was on the screen. It's the same. You're asked about if you repeat the experiment on the moon, it's the same. The trap is they want you to think it goes further on the moon, right? You see the astronauts bounding on the moon and they're going far, right? And that's the trap. But you got to come back to your evidence and reasons, the same as. Still energy conservation. G on the moon, although different, is still constant. It's going to yield the same effect, right? So you can derive all this again. I just said, as identified in part B, change in D equals 2 square root h1 times h2. Change in D depends only on the change in h1 to determine the final velocity. Change in h2 to determine the time. You're good. College Board, again, likes the claim evidence reasoning. I recommend that you set it up like that. All right, teammates. Send your cards and letters if you got any questions. Have you a great day.